Okay. So definitively for the test, there is something like this, right? So you have a charged particle entering an electric field. Remember, if it's negative, it wants to go against the electric field, but the force equals QE. So the force is parallel to the electric field, okay? It's proportional. So the force will be along the electric field. And if it's positive, it wants to go with the electric field because it has a positive sign. But when you have something F equals QE, it means that the force is along the electric field, right? So if F equals QE, that means those two vectors are parallel to each other. So they are collinear. So if you have something here with a velocity here, let's say this is negative, okay, and you have an electric field going this way. So electric field always starts from plus, goes into minus. Now the minus could be the infinity, could be very far away. So negative wants to go against the electric field. So it means that the force applied will be this way. That will be your force here. So it's along the electric field, but it's against it. So he wants to do two things. He wants to keep going along a straight line at a constant speed, but at the same time, it's going to accelerate down. So it's like a projectile motion. And then you're going to have something like this. Okay, so that's what we did that last time. And you can review that. And I think we were almost done here. So that's here, there's a mistake. This is delta Z. So the displacement along the Z-axis. And you see along the Z-axis, it's moving at a constant speed. There is no acceleration because there is no force. So we found that the time was about 5 seconds, if I remember. So you see delta Z. So if you want to find delta Z, so delta Z, the displacement along the Z-axis is just the velocity here that does not change along the Z-axis times the time. And you can compute that. Okay? So it's like projectile motion. So if it's negative, imagine the ground will be positive, right? It's a positive. If it's positive, the ground will be the negative side. Okay, so we did that. And if you open your book, you see you can get the PDF. There is a way to get the PDF, or you can find the PDF. It's not that expensive, $35 or even less. And that problem here, 21.7, it's a good practice. So what do you think is going to happen here? Is it going to slow down or accelerate? Accelerate, very good, right? The force is down, so the acceleration is also down. F equals ma, so it's going to accelerate. Now, I always have one problem. I don't know if it's for the test or assignment where I try to trick you, because here you have positive and you launch a negative. Okay, so if you launch an electron from here, it has some momentum to begin with, but it's going to slow down, stop, and then come back. Now, if you give enough momentum, it will crash. But not enough momentum, it will go up like this, right? It will go up, slow down, stop, and then accelerate again. Okay, so it's very important that you open your textbook. This is a very nice one for those who want to go into engineering. You hide. The idea is that you hide the solution and you try to do it on your own. Okay, what else? Okay, so if you want to curve your enthusiasm, no, we don't want that. We can visualize an electric field here. So these are simulations by MIT. So do you see how the two electric fields from this one and from that one, they interact with each other? So do you see that they try to connect with each other? So do you think they have the same charge or opposite charge? They seems to really like each other. Huh? Opposite, right? They want to combine, but they can't because this one has momentum, right? So it's just passing by. If it doesn't have momentum, it just crash on it. But you have to think as of the electric field like something like an aura, like a field, like a magic field, right? What about this one? Are they opposite or same? Very good. You see, it's like two springs pushing against each other. They're interacting through their electric field. So we call the test charge is then when the electric field of this charge here is so small that you don't see the disturbance, but otherwise they do interact with each other. And here you have angular generator. So are the charge the same or they repel, right? Now we're going to define in the next unit what we call the flux. Okay, so the flux in physics or hydromechanics, like mechanics of fluid, will be like how many lines, of this field will go through a unit area. Okay, so you take a unit area here and you see how many field lines are going through it. So you can imagine this is like a fluid flowing and you have an invisible net, okay, and you are catching those lines. So that will be defined by the flux, the amount of field lines going through a unit area. So we're going to define the magnetic flux, the electric flux, okay, and that will be attracting. You see, they try to connect with each other. The thing that you have to understand, an electric field always starts from plus, ends on minus. So if I take a positive charge here, the electric field starts from plus, and far away you have the ground. The ground will be the minus. Now if I build a dipole, goes from the plus to the minus. No electric field line intersect with each other. The number of electric field lines depends on the charge, right? So if I put here, if I put more charge, if I make it more Q here, you're going to have more field lines coming from it. Okay, so this is called the source, and this is a sink in mathematical terms. So that means you can define what is called a divergence. So that will be positive divergence, that will be negative divergence, right? Connecting to calculus. Okay, what's this? Any question? Okay, so we did that. Okay, let's review quickly some calculus. I told you in Dropbox you have two tutorials. One is about the dot product and one is about the cross product. So for example, if you are crossing two vectors, vector A and vector B, you're going to get a third vector, vector C. So you have to use your right hand. So either you say A cross B, and the angle between them does not have to be 90 degrees, right? Equals C. Or you can take your hand, this is A, I'm going toward B, that's going to be C. Yes, this is called the cross product. If the angle between them is 0, so if they are aligned with each other, then it equals to 0. Because you see that will be the magnitude, so sine 0 is 0. If it's 90 degrees, so A, B are 90 degrees apart, then that will be the maximum cross product that you can get. Now you can have the dot product. So that will be the definition of work in physics. You dot the force and the displacement. Okay, and it's a way to find how aligned two vectors are. So if they are aligned, you're going to get the maximum cross product. If they are perpendicular to each other, then it's going to be 0. So that will be the magnitude. And you can use components as well. That's the magnitude. Or then here you can pull your hair to find the components as well. Okay, and definition of a unit vector, just to make sure you remember from last semester, maybe. You see, this is a Coulomb's law. Okay, so the electric force is proportional to the product of the two charges, inversely proportional to the distance squared. This is called a unit vector. It's going to show you which way. It doesn't have any magnitude, just to show you the direction. Okay, so sometimes it's called r hat, and sometimes they have x hat, y hat. Okay, so just to make sure you understand, it's a review. For example, if I have a vector this way, I call that vector r. Okay, you see that the magnitude of r is 3. You see, 1, 2, 3. 3 what? I don't know, meters, for example. Yes? So I can define the unit vector with the same direction. I'm going to call that r hat. So the direction is the same. The magnitude is 1. That's why it's called a unit vector. Okay, so I can say the vector r is 3r hat. Okay, so how do we find that r hat? We can say the unit vector is just the vector r divided by its magnitude. Do you agree? So, for example, if you have a vector, I don't know, 2 and I don't know, I'm just making things up, 2, 3. Okay, so that means the vector, you start from the tail. So here, 1, 2, 1, 2, 3. Okay, so that's going to be 2, 3. So the vector will be this. That will be your vector r. Okay, the magnitude is 2 square plus 3 square. Is that 13? Square root of 13. Okay, so how do we define r hat? It's going to be that vector here. So I'm going to write. So sometimes the notation will be 2i hat plus 3j hat. It's just a notation for the coordinates. Okay, so this is I hat and that's j hat. Divided, so no, sorry. So this is the vector r. Do you agree? It's just a notation. So the 2 and 3, and that's another notation. Yes? So r hat will be the vector r divided by the magnitude. So it's going to be 2i hat plus 3j hat divided by 3. Okay, so that's how we define the unit vector. You just divide by the magnitude as I've shown you here. Agree? So just a review. So for example, r hat, you can say coordinate 2, 3, and 3 divided by 3. Because if you look here, okay, so this is 2 and this is 3. That will be r hat, the unit vector, and not exactly on scale. Okay, is that clear? So it should be 2 divided by 3, about here. Okay, so that's how we define the unit vector. So unit vector, here, for example, if you have this vector 3, 4, 10, you can find the magnitude. Once you have the magnitude, you can find the unit vector. So you take these same coordinates and you divide by the magnitude. So that will be the coordinates of the unit vector. Agree? And the unit vector is just showing you which direction it is. Okay, okay. Let's just coordinate of vector, just to make sure you remember. Let's say I'm doing you do the vector A, and then A is 1 0, and B is gonna be something easy, 0 1. Okay, so I'm gonna make a vector AB. Can you find the coordinate of the vector? So to find the coordinate of the vector, okay, you start always from the tail. So you have the vector AB. That's my vector. Let's say it's a vector displacement. How do you find the coordinate of a vector? From last semester, you go always start from the tail. This is the tail, this is the head. So you make a X, Y coordinate system, another one. And then what? So then you go from the tail to the head. So what's that? In that coordinate system, what's going to be the run here? Yes, one to the left. So it's going to be what? Huh? -1. So you go from the tail to the head. That's how we find components of vectors. You go from the tail to the head. You run, and then you rise or you fall. So in that case, you run to the left, it's going to be -1. And then what? You go up or you go down? Up. You go up by 1. Okay? So that's how we find coordinate of vector. So any vector you can paste, cut and paste, right? So I can take that vector, I can cut it here. If I want to find its coordinate, this is the tail, this is the head. I attach a cross to the tail so it doesn't fly away. I go from the tail to the head. You run, that's going to be its X coordinate. And you rise, that's going to be its Y coordinate. Okay? Agree? That's just a review. So we have this vector A, B. Can you find the unit vector? Okay, so the unit vector, remember, is just the vector divided by the magnitude. So what's going to be the magnitude? So this is what? Huh? Square root of 2, right? So the unit vector will be -1, the square root of 2 here, and then 1, and then the square root of 2. I'm just applying this. What's the meaning? It means that will be here, you have a hat here, and the magnitude is 1. Agree? So just a review. So r hat, we can say it's -1 square root of 2 I hat plus 1 over square root of 2 j hat. It's just a different notation. That means this is x, and that means this is y. Okay? Because if you have a x, y coordinate system, here you have, this is called I hat, sometimes it's called x hat. This is j hat, and sometimes it's called y hat. And then along the z, it's k hat. Okay, it's just a review from last semester. Any question? Okay, so you have your answer here. Left up. So it's a minus, so I guess that will be this one, right? Have to go to the left and then you go up, so minus and plus. If you need to review, there is a very nice simulation here. Okay? Let's keep going with the math. So we're going to define lambda. It's called the linear charge density. So it's going to be equals to, so if you have a line here, and because so far we have seen distribution of discrete charges. Now we want continuous distribution. So that means you cannot tell apart those charges because they are so small. Okay, so we need to define density. So that means you take a line here which is charged. So for example, in a Xerox machine, you're going to have this charge. It comes from a wire. The wire is charged and then there is a discharge on the drum. So you can define lambda will be the total charge here divided by the length, okay? Or okay, you take a little bit here, a little bit of dq, so infinitesimal, so it's like a little charge here, dq, over a little segment here, dl. So that will be the charge per unit length. This is lambda. Okay? Likewise, we can have sigma, which is the charge per unit area. So for example, if I take a Van Graaff generator, you have a globe. This is a surface. Okay, it's a surface, it's 2D. So we can take a little piece of it here and find how many charges you have here on that little area delta A. So sigma will be dq over dA, or the total charge, like 3 nanocoulomb, for example, over the total area, which is 4 pi r squared. Okay? So how much charge on a unit area? And then you can define ρ, which is, so in that case, it's a solid, right? And so that will be the charge per unit volume. I'm sure you do that in chemistry when we find the density, like the mass density, right? So volume you have to imagine as like something. Imagine you have a volume and you have the charges inside, embedded inside. So you take a little piece inside and you find how many charges per unit volume. So 1 meter, 1 meter, 1 meter. By the way, keep in mind that you can have charges inside an insulator, but you cannot have charges inside a conductor. If you have a conductor, like the simulation with John Travolta or John Volta, I don't know how they call it, the charge always goes on the outside of a conductor. They cannot stay inside. So that's why if there is lightning outside and you are inside your car, you're safe as long as you don't step out and don't step in water, because the charge will always go on the outside. Insulator, you can do that. In engineering, you can embed charges inside. Okay? So then the issue is going to be we have to use calculus to find the electric field at a given point. Have to use calculus. So it means, for example, at that point P, okay, you want to find the electric field. So then you're going to use the vector sum of all the electric fields generated by each little delta Q. So it's a sum. You are using the superposition principle, so it's a vector sum. Okay, so you are doing the sum and you scan. It's like you scan inside every little piece here. You scan, you find the distance. Okay, and you have to add not only that, but you also have to remember it's a vector. So you are adding vectors. So you have to add the x component, the y component, find the magnitude. And then because it's a continuous distribution, the sigma, yes, it's a sigma, right? The sum will turn into an integral. Okay, so with an integral, you want to make sure to have the right integration variable. So it could be a line integral if you have a linear distribution. It could be a surface integral if it's over a surface, or it could be a triple integral if it's over a volume. Are you with me? So if you have a line distribution, okay, so it will be something like this. So usually, let's say you have a long wire. So let's say this is a charge wire, like you have in a Xerox machine. You see the electric field, this is positive. Let's say it's positive. You see the electric field will look like this, from the plus to the minus, and then you have fringe effect. So you still have some kind of wind, right, being blown away. If it's negative, it's coming inside, but that will be the structure of it. So used to have a very nice simulation, but they remove it. Okay, it looks like this in 3D. Okay, from the plus to the minus, minus will be far away. That's what it looks like. So how do we do that mathematically? You have to think scanning. Okay, so it goes, you scan this way. So here, that little dq, okay, which is lambda dx or dl. Okay, dq is lambda dl, the amount of little bit of charge. Okay, it's going to make a small electric field here. And then that one, and then you scan, you go to the next one, and then it's going to make another electric field here. So you scan through, this one is going to make another electric field. And you see, if it's long enough, you have a symmetry. And you see when you add up all those little TE, okay, which component will cancel out? Because you have this one that way and you have that one that way. So can you see the X component cancel out? And only the Y component build up. So at the end, you're going to have a large electric field here. Okay? And you need to add all the Y components. Yes? 86. So here I have another. So usually it's done. You see, it's done by a program coding, Python, for example. Okay, and you came up with this configuration. So it's a vector field because every single point in space is associated with a vector. So that will be the electric field. So how we do that? So first of all, you can use your equation sheet where you have most of the distribution for continuous distribution. So for example, here, line. So in that case, you have a wire infinitively long. Okay, so very long compared to what? Compared to the electric field, the point where you are looking at, right? So not very long. And you see it's going to be lambda 2 pi epsilon 0, and then it's inversely proportional to the distance. Okay, how did they do that? You open your book and you do the math, and the integral is not that hard, but you can find this equation, right? So if we have a very long wire, okay, with a continuous distribution at a point P, the electric field will go this way because the X component from that one and from that one will cancel out, and that will be the magnitude. So again, lambda, it's the charge density. So it's the total charge here, total charge divided by length. Okay, or dq over dl, and that will be the distance r. That will be the distance r. Agree? Okay, so if I go back to that you are applying calculus 3 or 4, whatever calculus it is, but you see the electric field is this way. Because all the x components cancel each other, you add them up, and at the end, you're going to get a long straight. Okay, so how do we do the math? It's going to show you how to do the math. Yes.
You wrote that was equal to the E line equation.
Yes.
Okay.
The only if it says that the line is infinitively long. So that will be the magnitude here of the electric field at that place. Okay, so it will be lambda charge per unit length, and then r is the distance here, this distance there. Okay. So you have to do an integral from minus infinity to plus infinity. Okay, so for example, here we have an example. Okay, so we have an example here, you see, to see how it works. So this is not infinitively long. Okay, it goes from x equals a to x equals x plus l. Do you agree? So you're going to take a dx or dl. Okay, and the dq will be lambda dx by definition. You see, you're going to find what's going to be the electric field only produced by that little dq at that place P. So this is positive, so the electric field is moving away. So that will be a little dE. You with me? I don't understand. People take calculus and then there is nothing left. Okay, so this is delta E only from here. And then you're gonna find delta dE also from that one. So you're scanning hope. So that dE, that little electric field just from that one, you use the Coulomb's law, okay? So it's going to be dq, and then that will be the distance, that will be x here, distance squared, okay? But you have to scan rho. So you go from here to there, and the sum becomes an integral. So that's what you're going to get. So at the end, you have to find the integral, and that's what you get. So you should practice from your textbook, because it doesn't matter how much I'm going to explain it, you're not going to get it if you forgot your calculus. So it's better, and I'm not here to teach math, but you get the idea. So that will be the electric field here at that point. Any questions? So what's interesting here, what's going to happen when A is very big relative to L? Can you find the limit? So it's like the distance, that distance here is, so I'm very far away, so very far away. So, and I'm located here. So this is me here. And I'm looking far away. So from very far away, you see, I cannot even say that this is a line. From my point of view, this is just a Q. So can you find the limit? What's going to be left here? If this is big, big, big relative to L, A is larger than L, so it goes bye-bye. Okay, so the electric field will be Q 4 pi epsilon 0 A square, which makes sense because from very, very far away, you cannot tell that it's a line. From very, very, very far away, it's just a charge. Okay, you cannot tell that there is a distribution. You just say, okay, there is a charge. So if you take the limit, it's just going to be a charge Q, like we have done that before. Okay? Now, if the line is infinite, then you use your equation sheet. And then it says here for a line, that's going to be the equation for the electric field. So it's just the magnitude here. Are you with me? Okay, if you're not happy, it's okay. You blame the calculus, not me. Don't blame me. Okay, so at a very large distance, okay, even if the distribution is weird, everything happens like it's just a charge at a very large distance, right? So always the limit, when you take the limit, is just like you have just a charge because you cannot even tell the weird shape. You don't know if it's a line, it's a solid or what. Okay, also very nice, very famous. How do we find if the electric field at a point P, okay, from a distribution that looks like a ring? So this is a ring and this is charged. Okay, so let's say it's a conductor, you charge it, it's positively charged. So every single dq, so you divide it in little dq, every single one will make a dE. Do you agree? And then you go around and you add them up. And you see that when you add them up, there is a symmetry. And can you see that the y component will cancel out? Only the x component will stay. And how do we find the x component? So in that case, that will be the cosine. Okay, so the x component dEx will be dE cosine theta. And cosine theta is just adjacent over hypotenuse. That stay the same. Okay, it's easy. You should practice that because you're an engineer. So this is not even physics. Physics stopped here, and then it's just math. You see, you find the x component just for this one. Okay, you're gonna get something like this, and then you find the cosine to find the x component, and then you keep only the x component at the end. That's what you're gonna get. Agree? So I give you the result because before I used to go through the computation and I will lose like 3/4 of students. So it's no use. You open your textbook and you will see it's worth it. So anyway, that will be the electric field at a point P at that distance here, and the radius is A. Agree? And if you look at your equation sheet here, ring. You see, you have the equation for a ring. Okay, so the electric field, okay, along the axis, it's only along the axis because otherwise you need a computer, you need code, you need Python, whatever, or ChatGPT to do the computation. But that's only along the axis. A is the radius of the ring, X is the distance. Agree? And you see, you can even use, I don't know where I am. Just, okay, you can even use Wolfram Alpha to see what it looks like. So you say plot. We have an X on the numerator, right? Can you help me? Okay, ring, we have an X on top, and at the bottom we have an X squared. Let's take a fake radius of 2 to see what's going on. Okay, and then you do raise to the 1.5. Is that right? Okay, for x between 2 and 10, let's say. Is that right? So it's gonna go, it doesn't go up, it decreases. Did I do a mistake? Let's go back. X squared, 2 squared, 1.5. No, it's right, right? So the electric field is going to decrease. No, 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 no. What mistake did I do? For x between or zero, right? We should start at zero. Ah, you see, it's more interesting. We did that last time. So the electric field is going to increase as you move along the x-axis. It's going to reach a maximum. And then when you are very far away, okay, it's going to go as 1 over r squared, which is expected because at infinity, any distribution of charge behave like just one charge. So we expect that very far away, it goes 1 over r squared. Okay, so you are very far away. Okay, it will simplify as 1 over x squared. But first, it's going to increase, okay, at the distance equals to the radius about, not quite. Before that, okay, you will have to take the derivative to see the maximum. So you have to take the derivative of the function to see where is it, it's going to reach a maximum. So it's going to reach a maximum and then it's going to decrease. And that's how you have to think, right? You have to visualize what's going on. So what's going on? As you move away, the electric field is going to, so the electric field is what? X equals 0. What's the electric field? If x equals 0, what do you get? 0. Huh? X equals 0 is going to be 0. Okay, so the electric field is going to increase and then it's going to decrease. Agree? Right? That's not hard. That's very simple math. Okay, it's not even calculus. This is algebra. So this is the radius. You see, if x is very, very big relative to a, okay, so the electric field will be kxq, and then I have this one goes away, so x, and then times 3 over 2 goes bye-bye, so that will be kq x squared. Agree?
Yeah.
Okay. And again, I highly recommend that you open that website. Especially if you're an engineer, you need to know how to do the math, right? So you cannot survive without math. And you have your book, you need to open your book, blah, blah, blah. Because we don't have enough time together. So anyway, the electric field, you see, if you do the math, you take the derivative, you find the maximum, that will be the equation here. The maximum of the electric field will happen at r times square root of 2. So you can show that. You have to take the derivative. Okay, so let's try to do this one. So for this one, we're going to take a shortcut. Because what's happening here, it's a very, very long wire. So you should practice and do the integral and see if you get the same thing. But we're going to start with a shortcut. So I open my equation sheet here, open the equation sheet, and it says electric field of infinite line with no size. Okay, infinite or compared to what? Compared to where you are located. So you're going to use that equation here and try to do that. Okay, the equation is given. You don't have to do the integration. We can do it after and just answer. You just have to be careful with the unit. Nano is 10 to the negative 9. That will be the distance r at the point where your perpendicular bisector just at the center of the line. And you just use your equation, okay? And then I will show you how to do the integral, but just use the equation. And don't stare, okay? Staring doesn't help, do it. Bless you. So the magnitude of the electric field for a very long line is lambda over 2 pi epsilon 0 distance r. Remember that the electric constant is 1 over 4 pi epsilon 0, so you have different notation. K is 9 times 10 to the 9. Epsilon 0, it's the permittivity of vacuum, so it's 8.85 times 10 to negative 12. Okay, so we have a very long line. It seems that it's going to be positive. You have a point P, okay, and you have the distance here. That distance here, R, is 16. So this is the center. So even if it's not infinite, because you are at a bisector, it's fine, okay? Because you have the symmetry here. See, if you have like here, the electric field will go this way. Here, the electric field goes that way. So you only keep the y component. So that's why you can use that equation here. If you are at the bisector, and you see that the electric field will go up here. That will be your electric field. Okay? So you just plug it in. There is nothing to stare at. Just plug it in. Lambda is given. Coulomb per meters. And then that distance r is given. There is nothing to it, right? So the electric field will be, everything happens like it's because of the symmetry, you only keep the y component, so that equation will work. You plug it in. No, nothing scary here. Plug it in. Over, open the parenthesis, 2 pi 8.85 times 10 to negative 12 times 16. Nothing special. Newton per Coulomb. So the magnitude is 130. Did you put 8.85 times 10 to negative 12? 2 pi 7.9. What's your name? Andrew. Yes. So 7.9 Newton per Coulomb. Agree? What does it mean? It means if you place a 1 Coulomb of charge here, it's going to be acted upon a force that will push it away in this direction.
Can you say that one more time?
This is Newton per Coulomb. So if you place a 1 Coulomb of charge here, it will be acted upon by an electric force that will push it in this direction. So the 1 Coulomb of charge or any positive charge will accelerate in this direction. Okay, because the configuration is this, right? The electric field goes this way, electric field goes that way. So if you put a plus here, it's going to accelerate this way. That will be the acceleration. Agree? So that works because we took the bisector. If you don't take the bisector, if you try to find the electric field here, and this is not infinite, then you have to pull your hair and do the math, the calculus. Okay, because in that case, there is no symmetry. In this case, yes, there is a symmetry. If the wire is infinite, yes, there is a symmetry because the x component cancel out and you keep only the y component. Agree? Or you have to agree, huh? No choice. Say yes. Okay. So for example, if I want, this is alpha and this is alpha, and this is DE, so small e, so this is DE. So if I have to use calculus, you see that the electric field, it's going to be the sum of this electric field here, plus this electric field there, plus this electric field here, plus this electric field there. So you scan through. So it's going to sum of all the little y component, because x component cancel out. Okay, and so that's going to be the sum of the DE. That's going to be a sine alpha. Okay, and sine alpha will be opposite, which is 16 over 16 plus x squared. So I am not going to do the math, but at the end you have an integral. Okay, lambda 16 dx. That's going to be x squared plus 16 squared, 1.5. Guys, you can look at your book how they do it, okay? But otherwise you can get the same thing. It's just that we have the equation. You have to use integral. So when you use integral, line integral, you have to scan through. So I don't want to go into the details. Yes.
In the third line, what did you write in the radical?
Here,
Yeah, in the radical, 16 plus.
x squared.
Oh, thank you.
Yes. It's the hypotenuse. So this is x and this is 16. I'm pretty sure in the here you have the details in your book, and here this. So anyway, you get the idea, right? Okay, so let's choose again. Let's choose the equations again from your equation sheet. So we know the electric field from the ring. Yes, you take your calculus equation sheet from the ring, that will be the electric field. Remember, it starts from 0, it's going along the x-axis, it's going to increase and then decrease again. Do you agree? And from a ring, maybe I have a picture. Okay, look at that. So you see how it works. You have a ring. You divide your ring in small dq. Each dq, it's going to generate a dE, a small electric field. And then you scan. So this one is going to generate another one. This one is going to generate another one. So you have all those little electric fields produced by every single dq as you move around. When you add them up, you are adding vectors. So the sum of all those little electric field will be along the axis. Okay, so if it's positively charged, it's going to be along the axis after you did the integral. That's how it works. And so that was done with coding. I don't know which coding they did. But the electric field will look something like this. So along the axis, it's going to be like straight, right? So if it's positively charged, that will be the electric field. And then it gets complicated. Okay? What do you think the electric field here at the center is? 0, very good, right? It makes sense because it's going to be pushed by that one, so they kill each other out. So at the center is going to be 0, it's going to increase to a maximum, and then it's going to decrease. But usually we only stay along the axis because otherwise it's going to be very complicated, and it's only done with the computer, right? To estimate integrals, because otherwise it's too much math. Okay, so you have the equation for a ring, you have the equation for a charge, a single charge. Okay, so let's go back to this problem. Okay, so you can think about it. So now you have a charge here, Q, and you have the ring. So you need to add two electric fields. Agree? You're going to have the electric field from the ring, which is to the right, and you have the electric field from this charge. And we want to have the electric field equals to 0. So what do you think the charge is? Is it positive or negative? Negative, very good. It has to be negative, okay? So we have the electric field from the ring. And if the charge is negative, the electric field will go in. I'm going to call that EQ. So in that case, there will be a point where they cancel each other out and the electric field equals 0. And they want you to find that location. It's not that hard because you already have the equation for the ring and the equation for the charge. Okay, so you can help each other. What do they want? They want the charge Q. They want Q. They want this. So you can talk to each other, help each other. Okay, so what are the equations? Electric field from the ring in magnitude is Kx Q of the ring. We have Q of the ring. Here, 580 times 10 to the negative 9. This is A. And we have X. And a charge is KQ over X squared. Okay, so we want them to be equal to each other. Now, in this equation sheet, they give you with the epsilon 0. No, they give you with K. Okay, good. So we want them to kill each other. Okay, so that goes bye-bye. Nice meeting you. Okay, go. It's just it's not physics, right? Just solving. You are solving for Q. So what do you get? Okay, so Q is X. X is given 0.73. The ring is given, so 580 times 10 to the negative 9. x squared is given, so 0.73 squared divided by, open the parenthesis, x squared plus a is 0.71 squared and 1.5. And you can put cube here, 0.73 cube. Do it, take your TI. In nanocoulomb. Yes.
Where'd you get the 0.73 that's not squared?
X here. So it will be this. This is 0.73 meters, and this is 0.71 meters. Any question? Right, so what do you get? So you do 0.73 cube, enter, times, open the parenthesis, 580. It's not a 1 here, it's a nano. So nano is 10 to the negative 9. No, 10 to the negative 9. Enter, divide by, open the parenthesis, 0.73 square plus 0.71 square raised to the 1.5. And I found about 210 nanocoulomb. Did you get that? So 210 times 10 to the negative 9 coulomb. So 2.1 times 10 to the negative 7 coulomb. Agree? Did you all get that? 10 times to negative 7? Yes.
So the equation EQ equals KQ over x squared. Could you explain like the difference between the
Well, that will be the electric field from a point charge is this. This is just one point charge. That will be the electric field, which is the force per unit charge. The electric field from a ring, that will be the equation, that the one we did, because you have to take the integral. That's what you get.
I was asking why it's EQ equals KQ divided by x squared. I thought it was just like the force equals that. As I was confused. I mean, even notation.
No, the force. Okay, the force is this. Okay, so you have two Q. The electric field is the force per 1 coulomb.
Yeah, I understand. I'm just asking why it's E times Q, which equals. You know, like on the paper, like it's like you see how you have EQ equals K.
E ring equals EQ because we want them to kill each other, so the electric field equals to 0.
I think it's yeah. It's a notation.
Oh, maybe the notation. That means a point charge. That means the electric field from the ring.
Probably.
Any question? Okay, so this is a continuous distribution of charge.
Quick question for the first equation, like symbol that we was talking about, what do you cancel A out?
Okay.
A
What? A.
at the bottom of the denominator.
No, I didn't cancel. It's A. A is the radius. It's 0.71.
No, like before, like when you're writing the equations, you like drew like a line like that.
Okay.
No, for A before.
What do you mean?
Yeah, you said that like when X was like changing.
Oh, pourquoi they cancel out? Because it says that you want to find that place where the electric field equals 0. So we want the electric field from that one and the electric field from this one to kill each other out. So the magnitude will be the same because one is pushing to the right and one is moving to the left. Because we know that's going to be negative. So negative, the electric field is toward it. If it's negative, the electric field from a positive ring is moving away. And we want them to kill each other out. So the magnitude equals to 0. And that will be the electric field. Electric field is a force per unit charge. So if someone pulling me this way and someone pulling me that way, I'm not going to move. So the total force equals 0. So you add vectors. So 5 pounds to the right and 5 pounds to the left equals 0. Okay? Any question? Yeah. Okay, order distribution, even more interestingly, mathematically speaking, it's the disk. So it's flat. So now we have a surface density. It's not linear. The ring is linear. So we have a lambda. Now we have a sigma because it's a surface area. So we're going to define the charge per unit area. And how will you do that in math? When you take calculus, like you learn about line integral and double integral, what you do, you try to divide. Here, we're going to divide this surface area, which is a disk, into rings, okay? Because we already know the electric field of a ring. So we're going to add up, when we're going to do the integral, we're going to add the electric field from this little ring, and then that little ring, and then that little ring, because we go from 0 to R. Okay, so it's a typical approach in mathematics. So before I show you how to do it, because I'm not going to do it, because otherwise, again, everyone will be lost. You have to do it on your own, right? It's a very good problem. I want to show you what it looks like. This is the disk. Okay. So that's what it looks like. Okay. So you have a charge disk. So it's a disk. You already have charge it. So it's going to be a source for an electric field. And you have to use calculus to find the direction, the magnitude of the electric field at each single point in space. So it's going to be in 3D. Now, very far away. What does it mean very far away? It means the distance is large relative to the size of the disk, right? So very far away. Everything happens like it's just a Q. So it's going to be KQ over the distance squared, very far away. At a distance P, close. So now it's the opposite. At a distance small, compared to the size of the disk. So that's going to be very important. So I'm very close to the disk, okay? So then we can find the electric field. So this is called the charge disk. I'm skipping to the equation sheet. I don't know if I have another better distribution. No. So anyway, I'm skipping to the equation sheet. Here, I fix it, okay, because there was a mistake. It's going to give you the equation for the electric field along the z-axis at a distance z. And you see you have sigma, which is the charge density. Okay, so you already have the equation here, it's given. Now, I will just show you how to do the calculus, but I'm not going to do it, okay? Not calculus here, but you have the equations here. So in that case, along this x-axis, at that point P, you can find the electric field using calculus, and at the end, that's what you're gonna get. Yes.
So far away from the disk, you just use the K Q over R squared.
Very good,
If
yes.
you're close enough, then you actually apply the equation that applies to the disk.
Exactly.
Thank you.
Exactly. So the equation here. And we're going to find a limit when we are very, very close to it.
You know, when like what is to a pumpkin?
So far enough, it means that means the distance is large compared to the size. So if it's 1,000, if there is a ratio of 1,000, that will be large enough. If it's 2, if the factor is 2, that will not be large enough. But they will tell you how far you are. Yeah. So how far? Because in math, they just tell you take the limit when x goes to infinity. But that doesn't make sense in physics. So in physics, you have to say the distance is large compared to something. So in that case, will be compared to the size because we are in the real world. Yes, yes. No, same thing. Yes.
Does that only apply for this equation or for the other one? Like ring?
So always when you take, you can always take the limit. So if you are far away from the ring, okay, so in that case, x become large compared to what? To the radius. So a disappear, and we are get back to kq over r squared. So it applies to any distribution of charge if you are far away compared to the size. Okay, yes.
At point P, is that the only point on that like axis that the charge of the field is zero, or after if you follow that same axis, every point on the axis is gonna be zero?
No, so first of all, we choose along the axis because that's the only point where the computation is easy. But you can do the computation at other points, and then you see here that's going to be your equation. So do you think the electric field goes to zero here or no? No, it's not going to be equal to zero at the surface. So it's not like the ring. Okay, so I'm not so. So anyway, we're going to take the limit first, second. But first, I just want to show you how to do the math quickly. I mean, you can do that on your own, right? So you see, again, it's an integral, and they show you how to do it. Okay, so you have to take the ring equation, and then you keep adding up by taking the integral. Okay, so they show you the math here. So I'm not going to do the math. I'm sure it's done in your book. So let's take the limit, because in physics you are right, or in chemistry, what matters is always the limit. So very far away or very close. So let's see what's going to happen if we are very close, because it's easier to do. I don't know what's going on here. Okay, so this is the electric field here at a distance x. So here you have the electric field here at a distance x, and the disk is a source. So this is plus, 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 and you have a source of electric field that will look something like this. Okay, looks on both sides. You have the same thing. So let's take the limit so this is the radius r. I want to be very, very close to it, very close. So what does it mean very close? That means, yeah, so in math, you will say, okay, x goes to 0. In physics, we're going to say r is very big relative to x. Or x goes to 0. Right, so in math, you will say x goes to 0. So very close to the disk. Can you see what's going to happen here? So that goes to, if we are very close to the disk, x goes to 0. Do you agree? Okay. Or you can say that goes disappear, so those and goes away. So if x equals to 0, the electric field will be 2 pi k sigma. And that's going to be a very, very important finding, because do you see any X here? No. So when you are very close to this surface, then the electric field is the same. It's constant as long as you don't move too much away. Okay, so it doesn't matter if you are very close to this surface, the electric field will stay the same. We can make it a little bit more, we can change the notation. So K equals 1 over 4 pi epsilon 0. So then you have the electric field will be 2 pi sigma, it's the charge density, over 4 pi epsilon 0. So what you get? Bye-bye. Sigma over 2 epsilon 0. So that's going to be very important because when we're going to work on the capacitor, we're going to use that. So if you are very close, and it's not going to be true only for disk, any surface. Okay, so it could be, because if you are very close to it, do you agree that you cannot even tell that it has the shape of a disk? You cannot tell because it's so far. Or like imagine you are a little bug here. You cannot even tell how far it goes. So you don't know what shape it has. So it's going to be true even if you have something like this. Flat. Okay, if you have a square, okay, the electric field will look like this. Away, 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 very close to it. The magnitude will be sigma over 2 epsilon 0, and it doesn't depend on the distance. Are you with me? Sigma will be the charge per unit area. So if it's a rectangle, it will be width times length. If it's a disk, it will be pi r squared. But this is very important, okay? And so if you are not too far away, the electric field will stay the same. Now, if you want to see what's going to happen if you are far away, and if you want to use the math, then you have to use Taylor series. But if you use Taylor series, you're just going to find that very far away, it's just going to be k q over r squared if the distance is very, very large compared to a. But to come to this conclusion, you need to use Taylor series. You know, when you have a polynomial to the minus 1/2, so you have to expand it. So I'm not going to do that, but that's what we're going to get. So you can do that experiment. He did that experiment here. Demonstration. If I find him. Okay. Far away from him for studying. Okay, so the demo is amazing. Okay, he's very famous to have done those amazing demo. So it has an aluminum foil, which is the surface, right? So he's gonna charge it with a Van Graaff generator. So it's gonna be charged. And then he's gonna put like a small test charge, like ping pong ball, for example, with aluminum, okay? And it will test the electric field. And it's gonna show that if you are not very far from the plate, the electric field will be the same. You really have to move away, 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 so it's gonna start decreasing. So that means when you have a charged surface, okay, the electric field is constant as long as the distance is small relative to the area. It's a very interesting demo. It's a very nice demo.
So this is now charged, has the same charge as the plane. The plane is being charged, and here you see the angle. Try to remember that angle. hard to estimate, maybe 15 degrees. You see the vertical. It's about 30 centimeters away from the plane. Now I go back 50 centimeters, which is where I'm now. You see the angle hasn't changed very much. If I go further out to 60 centimeters, then the angle goes down a bit. Thank you very much. You now take the charge as being right at the center. I'll take the charge going first. Okay, so look at action.
It's a very nice demonstration. So this is it's like a point charge. So the electric field goes down as 1/distance squared. But if you have a plate or surface charge, then it will be constant like this, right? The electric field here will be constant if you are close to it, okay, at a small distance relative to the size. And the equation is epsilon here, sigma, which is the charge density in magnitude over 2 epsilon 0. And it doesn't matter the shape, okay? So anyway, I invite you to go here to look at the calculus because you are supposed to know. So if you have one problem like this for the test, I only want you to know how to set up the integral. So we'll take some examples, not to solve the integral, because I don't know how to solve integral without looking at Wolfram alpha or something like this. So I cannot ask you that from you. I think